Tonight, we are going to look at something that most of us take for granted. The colon. What does it look like? Just kidding. Probability and the binomial distribution. Okay, so to calculate the probability for an independent, equally likely event, I'm sure most of you have done this. What you do is you simply add up the total number of possible outcomes that you've got, and then you add up the total number of ways to get your desired outcome, and then you divide those two numbers. So, for example, if you wanted to know what the probability of drawing a jack from a deck of 52 playing cards is, then there's 4 jacks and there's 52 cards, so the probability is 4 out of 52. Or the probability of drawing a face card, jack, queen, king, ace, the probability of that event would be 16 out of 52. So that's how you calculate a basic probability, and I'm sure most of you have done this. Now, if you want to get a little bit more complex, you can consider things like rolling 2 dice. So you have 36 possible outcomes for rolling a pair of dice. And here I have in the column what number you would get on die number 1, and in the row up top what number you would get on die number 2. And then of course those two numbers would add to get your total roll. So here I have this sort of matrix with an array of possibilities that range all the way from getting 2 1s, which would give you a 2, to 2 6s, which would give you a 12. So there's 36 possible outcomes for rolling 2 die. And so if you look at it, the most likely event would be rolling a 7, okay? And that happens along the diagonal of our matrix here. So there's 6 possible ways to roll a 7. Okay, and there's 36 outcomes, so the probability of rolling a 7 is 6 out of 36, or 1/6. Of course, your least likely outcomes are rolling 2 1s to give you a 2, or rolling 2 6s to give you a 12, and there's only one way to do either of those things, and so your probability for that is 1 out of 36. So this is pretty standard kind of probability calculations, and what you're assuming is that these events are independent, that they don't influence one another, in other words, okay? So the fact that I roll a 2 on one die doesn't affect what I roll on the other die. Okay? Another example would be coin flipping, things like that. These are independent events. Okay, now let's say that you want to do the same action and you repeat it multiple times. And you assume that each repetition is independent of the previous one. Just like rolling the same die over and over and over again, the previous roll doesn't influence what you get on the next roll. Or flipping a coin, same kind of deal. If you want to calculate the probability for a sequence of events, then what you do is you multiply each of the individual probabilities to get your total probability. So, for example, if you flip a coin 4 times, the probability of getting any particular sequence, for example, I say here heads, heads, tails, tails, in that order, okay, then the probability of getting heads the first time is 1/2, times the probability of getting heads the second time is 1/2, times the probability of getting tails the third time is 1/2. So you see it becomes 1/2 to the 4th power because you're multiplying 1/2 4 times for each one of those things. Okay, now this may seem a little counterintuitive because we understand that if you're going to flip a coin 4 times, that the probability of getting 2 heads and 2 tails is larger than the probability of getting, say, all heads or, say, all tails. Okay, so that may seem counterintuitive because you're like, well, heads, heads, tails, tails, that can't possibly have the same probability as getting 4 heads. But in fact, it does. The difference is that there's more ways to get 2 heads and 2 tails. So for example, if I list out here, which I've done, all of the possible outcomes for flipping a coin 4 times, okay? So here H means heads and T means tails. So I can get all heads, I can get 3 heads and then a tail, I can get 2 heads, a tail, and a head, and so on and so forth, okay? So this is all my possible outcomes. There's 16 possible outcomes for flipping a coin 4 times, all right? Now there's only one way out of those 16 that you can get 4 heads. So that makes the probability of getting 4 heads 1 out of 16. But if you count them up out of that list, there's 6 different ways to get 2 heads and 2 tails because it depends upon the order in which it occurs, okay? So there's 6 possible ways to do that. So the probability of getting 2 heads and 2 tails, that's 6 out of 16, okay? However, it doesn't change the fact that the probability for getting any particular sequence is 1/2 to the 4th power, which is 1/16, which is the same as the probability for getting 4 heads, okay? Which is the same, in fact, as any of these individual probabilities, assuming a fair coin. All right, so that's calculating basic probabilities. Now the next step, we're going to build up through all these steps to a sort of understanding of the binomial distribution function. And we have to understand each one of the components that's going to appear in that formula. So basic probabilities and how to handle multiple events is one part of that formula. The next part of the formula is understanding how things are ordered. Okay? So let's assume that we have a number of objects, and we want to know all the possible ways that they can be arranged in a row. Okay, so for example, let's just say we have 3 people and we want to put them in a line. So just for simplicity, their names are Bob and Carol and Ted. Okay, and so we can write this all out, B for Bob, C for Carol, and T for Ted. And so there's 6 ways we can line those up. And I've listed them here. Okay, Bob, Carol, Ted, Bob, Ted, Carol, blah, blah, blah. Okay, all the different variations there. There's 6. Okay, now it's no coincidence. This is 3 factorial. And in fact, a factorial is the way to figure out the total number of possible ways to order any group. So for any number of objects n, the number of ways to order them or to line them up in a line is going to be n factorial. Okay, so the factorial, the idea of ordering things, is an important point in what's called the combinatorial function, which then appears in our binomial distribution function. So let me explain the combinatorial function to you. So probably the easiest way to understand this is to assume that you have like a hat or a big jar or something, and you're drawing out names for prizes. Okay. So for example, let's say that there's a pool of 100 people that have all put their names in this hat. Everybody's put their name in one time, and there's 3 equally nice prizes. Okay. So how many different possible combinations are there of ways that people can get prizes? Well, we're assuming here that order isn't important because the prizes are the same. They're the same value, monetary value. So it doesn't matter what order the names are drawn out in. Okay, so we're assuming order is unimportant. So if order isn't important, then that means that you're going to use that factorial function, right? Okay, so in fact, the combinatorial function is given here. You have the number of people in the pool factorial, okay, divided by the number of winners in the pool factorial, times the number in the pool minus the number of winners factorial. So for our particular example, the number of people in the pool is 100, so it's 100 factorial divided by, there's 3 winners, 100 factorial divided by 3 factorial divided by 97 factorial. Okay, and if you solve that for our particular problem, then you get 161,700 possible combinations of names that are drawn out. Note that this is very different from your probability of winning, which would be 3%. Okay, this is just the combinatorial function, which tells you the number of possible outcomes for that draw, if that makes sense. Okay, so now that we understand the combinatorial function, we understand the probabilities, let's put it all together and come up with our binomial distribution function. Okay, so this is used to describe a very specific set of circumstances, and that specific set of circumstances is as follows. You have n independent trials. Each trial can have various outcomes. We're going to call the outcome you're interested in a success. Okay? P is going to be the probability of success, and we're going to assume that the probability of failure is then Q, which is 1 minus P. Okay? Because the probability of something happening is 100% or 1. All right, so Q is the probability of failure, and now to calculate the probability of getting V successes in n total trials, you're going to use the binomial function. And the binomial function is given by that combinatorial function that I talked about earlier, n factorial divided by v factorial divided by n minus v factorial. And now times the probabilities of successes and failures. So for v successes, the probability would be p raised to the v power, and then v and q failures, okay, you have n minus v failures, the probability of q, so you have q raised to the n minus v power. Okay, so we've put it all together now. We've got what we know about the probability for n trials out here, where they're multiplying times one another, and then the combinatorial function because order is unimportant. Okay, so we're going to go back to our little coin flipping example, saying that we have flipped a coin 4 times, all right? So what's the probability of getting 2 heads in 4 flips of a coin, right? Well, in this case, we have 4 trials, so n is equal to 4, and the number of successes is the number of heads, which is 2, okay? So our function becomes 4 factorial over 2 factorial over 4 minus 2 factorial, and then the probability of success is 1/2, and we're going to have 2 of those. So you 1/2 raised to the 2 power, and then 1/2 is also the probability of failure raised to the 4 minus 2, or 2 power. And if you do the math, you can see that your probability is 3/8 as given by your binomial function. But this is exactly what we got when we worked it out by hand a few slides ago. We worked out that there were 16 possible outcomes and 6 ways that this could occur. 6 over 16 is 3/8, and so our math squares. Sorry about that. Okay. Now, let's do another example that's a little bit more complex. Let's say that we are playing Yahtzee. So, I don't know if you've ever played Yahtzee. It's very tedious, but it's great for probability and odds. So, in the game of Yahtzee, what you do is you have 5 dice, and you roll them simultaneously. And if you get all 5 dice on the same number, then that's a Yahtzee. Now, in the real game of Yahtzee, you've got 3 rolls to do this. But let's just, for the sake of simplicity, figure out what the probability is of getting a Yahtzee on the first try in 1 roll of those 5 dice. Okay, so let's figure it out as though we're going to figure it out for a particular number. So let's call it 5 sixes. We're rolling 5 sixes, okay? So the probability of rolling a 6, that's going to be our success, rolling a 6. And that probability is 1/6. So that makes the probability of failure 5/6, okay? And we've got 5 trials because we have 5 dice. And we want 5 successes. So n and v are both equal to 5. So when we plug in for our binomial theorem, we're going to get 5 factorial over 5 factorial times 0 factorial, and then 1/6 to the 5 power and 5/6 to the 0 power. Now, of course, anything raised to the 0 power is 1, and 0 factorial is also 1, in case you've forgotten that. So what we really get here is 1/6 to the 5th power, which gives us a probability of 0.00013. But there's 6 ways of doing this, because we could roll 5 sixes, we could roll 5 fives, we could roll 5 fours, etc. So we're going to take this number and then multiply it by 5, which gives us 0.00078, or a 0.078% chance of getting a Yahtzee on the first time. It's not very likely. That's why they call it Yahtzee. So anyway, you could use the same logic for rolling 4 of a kind or rolling 3 of a kind. It's the same kind of logic, except that your number of successes would change. Your number of successes, for example, for 3 of a kind, v would then be equal to 3, okay? But your number of trials n is still 5. Okay, so any kind of combination like that you can figure out. Okay, so that's kind of how you use the binomial distribution function. I want to emphasize that it is a distribution function, okay? So this is the only other distribution function, the first distribution function that we've studied so far, other than our Gaussian distribution function. So they've got tons of things that are different about it. They describe an entirely different set of circumstances. But they've got certain things in common because they're both distribution functions, okay? All distribution functions describe how data is distributed, and they give a probability for any particular set of outcomes or range of outcomes. That's what distribution functions do. And also, distribution functions should be normalized, which means that if you sum over all your possible combos or integrate your function over all space, your total probability is 1, or 100%, and that's what a normalized function is. And in fact, the binomial function does all of those things, so it's a distribution function. I also want to emphasize the importance in the binomial distribution function that the trials really do have to be independent, okay? So each one of those trials cannot influence further trials. And there's tons of examples in probability where this is not the case, okay? Dealing a poker hand from a deck of cards, for example, is not independent, because once one card is dealt, what's remains in the deck is completely different than what was there before. You started out with 52, you deal 1, now you've got 51, and the possibility of somebody getting that card that you just dealt is gone. So these trials are not independent, okay? These are dependent trials. Another fun sort of dependent trial example that I like to do is the birthday example. So how large is the class got to be in order to have the probability of finding two people with the same birthday of being at least 50%? Okay, let's forget leap years for just a second. This also is dependent. These trials are dependent, and let me explain why in the birthday example. Okay, so if you can figure out what the probability is that no two people have the same birthday, then the probability that somebody does have the same birthday is just 1 minus whatever that number is, okay? So let's figure out something that's slightly easier. Let's figure out the probability that no two people in a specific class share the same birthday. Okay, so if you start going around and asking the people, the very first person can have any birthday because nobody else has talked yet, okay? But then the second person that talks, if they're not going to have the same birthday as the first person, they only have 364 choices. And then the third person only has 363 choices, and so on and so forth. So what you get is a function that looks like this. Here's your first person that can have any one of the days, 365 out of total 365. Here's your second person that's only got 364 out of 365 choices, okay? And then 363 out of 365, 362 out of 365, all the way down to 365 minus n plus 1 over 365. So this is for the nth person in your class, however people might be in that class. Okay. Now, you can do a little bit of math and figure out that this is the same as the formula that I've written underneath it, which is 365 factorial divided by 365 minus n factorial times 365 to the nth power, okay? Now, if you solve and set this probability equal to about 0.5 or 50%, all you need is a class of 23 people. That's it. And then once you have a class of 23 people, the probability that any two people are going to have the same birthday is about 50%, okay? So that's how big the class needs to be. So it's kind of an interesting problem and an interesting example of dependent trials, all right? So the binomial distribution function is a very nice function, and it works very well for a very specific set of circumstances, but it only works for independent trials, not dependent trials, and there's a whole class of problems that will not therefore be solved by using the binomial distribution function. Okay, I have nothing else to say, and I am saying it, and that is poetry, and I'll see you in class.